Let's just start with the definition. A logarithmic scale is a scale of measurement, scale of measurement that is useful when data values are very spread out. Okay, when most graphs are made, a linear scale is used. The most common linear scale is 0, 1, 2, 3, 4. Okay, but it could be 0, 20, 40, 60, 80. It could be 0, 100, 200, 300. So anything that is linear. Okay, now a common logarithmic scale is 1, 10, 100, 1000, where now each preceding value is being multiplied by 10. Okay, another way that these are sometimes represented is as powers of 10. So like 1000 is 10 to the power of 3. 100 is 10 to the power of 2. 10 to the power of 1. 1 is 10 to the power of 0. Okay, so a lot of times logarithmic scales will be written that way. Okay, so let's take a look at some data. So consider the following data. It measures distances of space objects from the sun in millions of kilometers. Okay, so notice the objects that we have here are Mercury, Earth, Jupiter, Pluto, not a planet anymore, but a space object, Proxima Centauri, and the Andromeda Galaxy. So these again are all measured in millions of kilometers. Okay, so let's go ahead and graph the data on a linear scale. Okay, so what I have is a scale here. It's really going by 500s, and then every 1,000 is labeled. So I could start with Mercury. Mercury is 58 million kilometers from the sun. So 50 is going to be pretty close, probably be about here. Okay, Earth is 149. That's going to be right about here, so really close. Jupiter at 778. That's going to be about here. Pluto now is at 5,900 million kilometers. So that's going to be out here. Okay, and now notice there's no way I'm going to be able to fit these two things on this linear scale. I would need a much larger linear scale. Okay, so a logarithmic scale would work better to graph all of the objects. Okay, so now instead of just going by 500s or thousands, the way I have this lined up is these are all powers of 10. So it starts at 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, okay, and so forth. So now what I can do is I can use these values to better graph all of these numbers. Okay, so remember I know that 10 to the power of 1 is 10, 10 to the power of 2 is 100, 10 to the power of 3 is 1,000. Okay, so if I want to graph Mercury, Mercury is going to be about here at about 58. Okay, Earth is going to be at 149, so that's going to be a little bit above 100, so this would be Earth. Okay, so that's a little further apart than we saw on the linear scale. Okay, 778, that's going to be in between 100 and 1,000, so that's going to be about here, so that would be Jupiter. Pluto at 5,900, that's going to be between 1,000 and 10,000. So this is 1,000, this is 10,000, so that's going to be about here, Pluto. Okay, Proxima Centauri is 4.1 times 10 to the 7th, so that's going to be about here. And the Andromeda Galaxy is 2.4 times 10 to the 13th. So that's going to be about here. Okay, so notice that we were able to, even though these values were very, very far apart, using a logarithmic scale, we could graph all of them on the same number line to get a little bit of perspective. So the main idea here is to be sure you understand the scale before you interpret graph data. Okay, so it's really important that on this one, we can see that Jupiter and Pluto are very, very spread apart on this particular scale. Okay, when we go to this scale, You know, I would say that Pluto now in the Andromeda Galaxy was about the same size as it was on that distance, about the same size on the other scale, but obviously they're way, way further apart in practice. So it's just important to understand the scale before you start interpreting graph data. A couple other places where a logarithmic scale are used is the Richter scale. So the Richter scale is measures the magnitude of earthquakes, and the pH scale measures how acidic or basic a compound are. And again, both of those are logarithmic scales. Another set of data that could be graphed on a logarithmic scale is the number of transistors in an integrated computer chip over time. So in the 1960s, Gordon Moore of the Intel Corporation predicted that the number of transistors in an integrated computer chip would double every 18 months. This is known as Moore's Law and has largely held true. So just to kind of think about how that data might be. So let's just say that in the 60s there were 100 transistors in a chip. Okay, if that doubles every 2 months, or excuse me, every 18 months, in 18 months then it'd be up to 200. Another 18 months, 400, 800, 1600. Okay, and as we go, even just in 10, 15 years, you're going to end up with a very large amount of transistors. Okay, so we can see that because this data is going to be so spread out that we are going to need an alternate scale to graph this data. So in this case, a logarithmic scale would be another way of displaying this type of data. So that has been your tutorial on logarithmic scales. Thanks for watching.